Welcome to the video on fast Fourier transform. We have already discussed about the discrete Fourier transform in our last video. So the discrete Fourier transform, as we have already discussed, it can be used to perform linear filtering. So let us study about a set of algorithms which is actually known as FFT, the fast Fourier transform, which was proposed by Cooley and Turkey in the year 1965. The fast Fourier transform, it is a very efficient procedure for computing the DFT of a finite series, and it actually requires less number of computations than that of direct evaluation of DFT. It reduces the computations by taking advantage of the fact that the calculation of the coefficients of the DFT can be carried out iteratively. So due to this, the FFT computation technique is used in digital spectral analysis, filter simulation, autocorrelation, and pattern recognition. The FFT is based on decomposition and breaking the transform into smaller transforms and then finally combining them to get the total transform. It actually reduces the computation time required to compute a discrete Fourier transform and improves the performance by a factor 100 or more. This actually involves in the direct evaluation of the DFT. Now we have problems. So this is the formula to find the DFT. So summation n is equal to 0 to n minus 1 x of n e power minus j 2 pi kn by n, where k expands from 0 to n minus 1 and this capital N is the number of samples. So there are two methods in FFT algorithm. One is decimation in time FFT and decimation in frequency FFT. Now let us see a simple example on DIT FFT method, that is decimation in time FFT method. If you see the question here, it says compute the 8-point DFT of the given sequence 2, 1, 2, 1, 1, 2, 1, 2. So the first step is you should take the FFT in the bit reversed order. The input should be taken in the bit reversed order. So bit reversal is done. So we have the first stage computation. So in the first stage of computation, there is only one twiddle factor, that is e power minus j 2 pi. So n here it is 0, so 0 by 2. So this becomes e power 0, which is equal to 1. So there is only one twiddle factor. So we do the computation with the twiddle factor as 1, and finally the output of stage 1 is obtained as 3, 1, 3, 1, 3, minus 1, 3, minus 1. Next we move on to the second stage of computations. Here we have two twiddle factors. So e power minus j 2 pi 0 into by 4, which becomes e power 0, which is 1. 1 is the first twiddle factor. Second, for the same expression you substitute here instead of 0 you substitute n is equal to 1, then you get e power minus j pi by 2. So this can be expanded as cos pi by 2 minus j sin pi by 2, which is actually cos pi by 2 is 0. Sin pi by 2 is 1, so we get minus j. So the twiddle factor for the second stage of computation is 1 and minus j. So keeping this, we have calculated. So the output of stage 2 is obtained as 6, 1 minus j, 0, 1 plus j, 6 minus 1 plus j, 0 minus 1 minus j. So the output of the stage 2 will be taken as input for stage 3. So in stage 3 we have four twiddle factors. So in this we put first expression, we put substitute n is equal to 0, we get e power 0 1. Next we put 1, we get e power minus j pi by 4. We expand this cos pi by 4 minus j sin pi by 4, which is actually 1 by root 2 minus j 1 by root 2. It is obtained as 0.707 minus j 0.707. 1 by root 2 value is 0.707. Okay, so the third twiddle factor is minus j, and the fourth twiddle factor is minus 1 by root 2 minus j 1 by root 2, or we can write it as minus 0.707 minus j 0.707. So keeping these four twiddle factors, we compute the third stage and the output is obtained.